Hello everyone, let's welcome our next speaker, Dimitri and Michael, who will be talking about finding backdoors using fuzzing. It's your turn.
Thank you so much. Good afternoon, everyone. So I'm Michael Marcosi. I'm a researcher at University of Paris-Saclay in France. And so, yeah, it's my very great pleasure to be here in FOSDEM' to tell you about our tool, ROSA, which you can actually find on GitHub and which is about finding backdoors with fuzzing. So this is a joint work with Emilia, Stefano, who's just there, and Dimitri, who's the main developer of ROSA. And so, yeah, I will actually start the talk by giving you a general overview about what ROSA is about. And then I will leave the floor to Dimitri. We will give you more technical details, make a demo of the tool, and talk about the performance of the tool. So let's start by actually presenting you what we mean by backdoors and fuzzing. So what is a backdoor? When we've started this work, we saw that it was, we had a simple definition of it. But actually, as we started digging, we realized that people could mean really a lot of different things because they can be backdoors in many parts of IT systems. So for example, it can be like a server which has been weakly configured on purpose so that people who are aware of that can use it to get access to the server. It can be like you have a machine learning model which is used to authenticate people, and some guys have poisoned the training data so that they will always be authenticated. And yeah, it can happen. It can be also like in cryptography, some mathematical flows that have been planted in the algorithm itself, in the math of the algorithm, so that if you are aware of this flow, you can actually decipher more or less everything that is encrypted with this algorithm. And there are other kind of backdoors in the IT stack. But in our work, we focus on what we call code-level backdoors. So the idea is that you have like a hidden access, which is hard-coded in the program code. So the idea is that you have to feed the program with a given input, a secret input value that you have to know. And if you give the program this input, it will give you like it will enable you to bypass the authentication mechanism of the program, or also to give you access to like underlying system resources like a shell. And yeah, examples to make things a bit more clear. For the first case, like let's imagine the program is sudo that you use to get root access on your machine. So the backdoor could be like a password, a key password that has been hard coded in the code of sudo, so that like if you run sudo and use this password value, you get root access and can run commands as root. For the other example, the program could be like a web server, and if you send an HTTP request with a given argument value, a secret value, it will create a reverse shell, and you will have, for example, root access to the machine where the server is deployed, and probably to the private network behind this machine. And so, like, this is not just like academics like us dreaming in their ivory tower. This is a real issues. So there have been real examples of such backdoors injections. So you guys probably have heard about the famous XZ backdoor injections, but it's just the tip of the iceberg. There have been other documented cases like backdoors in PHP, VSTPD, ProFTPD, and also, like here in FOSDEM, we are more about open source software, but there are also a lot of backdoors that have been found like in proprietary binary firmware of devices like routers and this kind of stuff. And in all these cases, you have what we call the butterfly effect of supply chain attack, because the idea is that if you plant the backdoor at the right place in the supply chain, that it will infect everything above. Like in a router, you plant it in the firmware, and all the people who get this router get the backdoor. If you plant it like in XZ, all the software which reuse XZ will get the backdoor actually. So it's really bad. And so to solve this problem, the technique that we have decided to use is graybox fuzzing. So basically, it's kind of brute force testing of programs, but with more or less randomized inputs that you send to the program. But it's a bit more clever than that, because you have some kind of a feedback loop that try to cover more and more parts of more and more branches in your code, actually. And actually, it's coupled with a simple mechanism to detect code failures, which is just crash detection. But in this way, you can still, with some sanitizers, for example, you can detect a lot of memory errors, like buffer overflows, and that all this kind of stuff. And so, like, it's a line of work that has gained a lot of tractions with some modern fuzzers like AFL++, which we are using in this work. It's been gotten quite popular for a few reasons. First, like, they have a good track record of finding CVEs in many different kind of codes. They are efficient for exploring different sources of program, including source or binary-only programs. And they've mitigated what in the community we call the magic byte problem. So the idea is that if you do some kind of randomized testing of a program, maybe at some point in the code you will have an if statement saying if this part of the input is equal to this long stream of bytes, then you can enter inside the if statement. And obviously if you are trying to guess the right value to enter there by randomized testing, probably it will never happen. And so you won't test this brick part of the code inside the if statement. And now, like modern fuzzers like AFL++, they have mechanism to quickly analyze the code and recognize such hard-coded magic bytes value. So yeah, that was a bit what we meant about what backdoors and fuzzing are. And now let's discuss our work to try to detect backdoors with fuzzing. So when we started this work, our the use cases that we had in mind were more or less like vetting, people willing to vet like some third-party components like libraries or firmware from some routers that, yeah, they wanted to include in their infrastructure, so they want to put the library in their software or a router model in their network stack, and they want to make sure that the software is free of backdoors. And yeah, now currently we are working on another use case, which is trying to prevent the injection of backdoors, like in open source project, like at a CI level, like having some commit vetting mechanism that try to detect that at some point one guy tried to inject a backdoor. And yeah, if you want to, this comes with other challenges, and if you want to know more about that, just come tomorrow to our talk in the CI and testing track, where Dimitri will tell you more about this slide. So that was our use case, and to try to solve this use case, we started by looking at what more or less was existing, and what we found it was mainly like manual code reverse engineering to try to find a backdoor in the code, but obviously that's really royal pain, and so most of the times people don't do it. And there've also been a few tools that have been developed to do that, but it's basically just trying to automate a part of the manual engineering effort, and actually these tools they are actually gathering dust, so most of them are not available anymore, or they are available but they are not maintained and they don't work. There was just one we could try, but the results were a bit terrible. And also another problem that we noticed is that there is a limited backdoor sample availability problem, because the report about backdoors are rare, and when you get one, it's usually like about artifacts that are lost or that do not work. And so this is painful, because if you want to create a technique to develop to detect backdoor, at some point you want to test it to see if it works and detect real backdoors, and if you don't have samples, it can be a bit annoying. And so yeah, given that there was room to do something better, we decided to go with graybox fuzzing, because it's largely automatic, so it's better than just doing some manual stuffs. It can explore all types of program, including if you want to vet like a binary firmware. And yeah, it has already been very successful to find CVEs like buffer overflow, so why not finding backdoors? Actually, there is a good reason, is that actually they just can't, out of the box, they can't find backdoors, because what they detect is crash. They detect if the program crashes when you test them. But usually, if you've done your backdoor well, it won't crash, because otherwise people will notice it quickly. So obviously, it won't work to detect backdoors in that way. And the big challenge in our work was to find a way to teach the fuzzer to recognize that at some point during program execution, a backdoor triggered. So that was the big deal of our work. And yeah, here comes here come the contributions of our work. So the idea of ROSA is to take out of the box a graybox fuzzer called AFL++, and to couple it with a mechanism called metamorphic oracle that actually enables detecting that a backdoor is triggered. And yeah, I will just give you the intuition, and then Dimitri will go into the details. So the idea is that if you fuzz, for example, sudo with only wrong password value, you should observe always the same kind of behavior like sudo saying the password is wrong. But if suddenly your fuzzer find out the hard-coded password value, suddenly you will see something totally divergent, a divergent behavior like a new process being created and other stuffs. And it's from this divergence that, through this divergence, that the fuzzer can detect the backdoor in ROSA. And so the other things that we have introduced is ROSA Room, which is a long overdue standardized backdoor benchmark with 17 programs, 7 with authentic real backdoors from real attack that we have found, and 10 where we have asked a researcher to inject synthetic backdoors in popular open source programs. So yeah, now Dimitri, the mic is yours so that you can give the technical details.
All right, so let's go over a real example to see how ROSA works, right? So there's this Belgium router model that is fairly popular. And people have figured out that it runs a BOA server, so they did this by manually digging into the server. This BOA web server seems to not be maintained anymore, but Belkin used it at the time by adding some stuff on top of it, and people actually figured out that they've added a backdoor in the server. So how does ROSA detect this backdoor? Well, ROSA works in 2 phases. So there's a first very short phase where ROSA just runs a fuzzer and discovers what we call the representative inputs. So those are the most common inputs to the program. So this is an HTTP server, so the fuzzer generates HTTP requests. Let's say it first starts with a GET request at the root of the server. That yields some control flow graph edges in the server program and also emits some system calls. And that is saved in a database. And the fuzzer goes on. Maybe it manages to modify the string a little bit and generate a post request that yields slightly different edges, so that's a different input, so that gets saved, so on and so forth. And then very quickly, after about a minute, we switch to phase 2, where the fuzzer now intensively explores the program, and every new behavior is vetted individually. So let's say the fuzzer, again, mutates the input a little bit and hits this other endpoint, and that produces some system calls. So what we do is we first choose the most similar representative input from the first phase. So let's say that it's B in this case, and we compare the system call vectors. And if they're the same, then the behaviors are equivalent. And since the representative inputs are considered to be benign, then we can assume that input C is also safe. So that's fine. But at some point, due to what Mikhail said, due to the guiding, the fuzzer will end up hitting some hard-coded endpoint that is special in the server, and that will produce some different system calls, right? So again, we'll do the same thing, which is the most similar input. Let's say it's A from the first phase, and the behavior is no longer equivalent, so this is suspicious. This might be a backdoor. But this alone does not prove that there's indeed a backdoor, so a human expert has to vet these findings, and there's a semi-automatic method that allows us to do this fast. So what you do is basically you take the divergent system calls that ROSA gives you. In this case, there's 56 and 59. If you know your system call numbers, you know what those are. And you run that through strace, and then you look at the actual log that strace gives you, and you can basically immediately see that there's a fork and exec of bin sh, so reverse shell on the server without authentication. So obviously, this is not right. So let's actually do this in practice. So huge disclaimer, we've biased the fuzzer a lot here for the purposes of the demo to go faster. So this usually takes about 4 hours, but most of the overhead is about emulation. We can talk about it later if you want. So let's do it. So I have here a part of the HTTP server that we've decompiled, and if we open it up, so this is decompiled code, right? So it's going to look ugly, but basically they've added this bizarre function on top of the server, and if we scroll down a little bit, at some point there's a system call that seems to arbitrarily execute some command, right? So, but we don't know that yet. We don't want to have to reverse engineer the server. So how could we find that with ROSA? Well, ROSA only really needs a simple configuration file to work. Fuzzing is pretty easy if you've done it before. And there's a wizard basically to generate that config file. It's just a simple TOML file that mostly describes what settings to use in the fuzzer, but that is automatically generated. And if I run it, we can see ROSA in action. So it will spin up the fuzzers in the background, and it will start trying to find the backdoor in the actual program. So the interface looks like a fuzzer. So we built this with Ratatouille, if you're familiar. It was really easy to build. And the goal here is, again, to collect some representative inputs first, which it's already done. And now we're trying to see if there's any suspicious behaviors in the program. And it should find a backdoor. Drum roll. If not, I'll rerun it. But so yeah, fuzzing is not easy to coerce. But yeah, basically you have a bunch of stats, and what interests you most is the top right quadrant. And there we go, backdoor found. So I'll stop it here. All right, so all of that data, of course, is persisted to disk, so we can look at it at our leisure. And so there's this output directory, and if I look into it, there's a bunch of stats. Again, if you've used the fuzzer, this should look familiar. So what I'm interested in is the backdoor subdirectory, which stores inputs that lead to suspicious behavior. So let's look at what's in there. So there's one input that was saved. It's saved in kind of a weird way because we duplicate findings as much as possible so that you don't have to look through a ton of them. And how do I know why this is suspicious? Well, there's a nifty little tool called ROSA explain, where if I give it the name of the input, it will explain why this is a backdoor. So basically, it says that it's a backdoor because it found these system calls with this input, but not with the closest representative one. So again, I will do what I explained before. I will run this through strace, and I will only feed it. I will tell it to only filter these inputs and to use the backdoor input that I found before. This will run it through strace, and now I can look at the log. And the log starts with the QEMU fork that AFL uses to run the fuzzer. And if I scroll down at some point, what do you know? There's an exec-v of sh something something piped into something something. That looks very fishy to me, so I'm going to keep looking. So actually, next thing that I'm going to do is I'm going to look at the input itself just to get an idea of what does the input look like. So the input looks like this, and again, that's very specific. I'm hitting a very specific endpoint, and I'm passing a very specific parameter to it. So let's try it for real on the actual server. So let's start the server. So this is as if it were running on the actual router. I'm going to hit the endpoint, right? So I'm just going to hit dev. Oops, I meant to do curl. Dev.cgi, and then I'm going to hit it with ID. Whoops, I'm root on the server. So I can run arbitrary commands as root on the server, and there you go. That's how you find the backdoor. All right, to wrap up, so we went through this effort to build this backdoor evaluation benchmark so we can actually see how ROSA fares in a variety of scenarios. And we use standard fuzzing evaluation practices to do it. The questions are, can we detect all of these backdoors in different scenarios with enough automation, robustness, and so on? And also, how do we compare it to existing tools? So as Mikhail said, only one tool is surviving, sadly, and that tool is a reverse engineering aid tool, basically. So we compare it with that one. So first of all, fuzzing is non-deterministic, so you have to run it many times to see if you actually can detect things reliably. And we detect all backdoors in the benchmark with an 87% success rate. So this is in line with most fuzzing approaches. It's actually a pretty good rate. Then in terms of time, it takes ROSA an hour and a half on average to detect a backdoor. This is largely due to the emulation overhead. And as you can see, the state-of-the-art tool is much, much faster because it kind of does a glorified grepping of strings, basically, in the binary. That allows it to go much faster, but it also cannot detect the vast majority of the backdoors because not all backdoors are built like that. And where ROSA really shines is the automation part, where it only reports 7 inputs to vet, like I showed you, semi-automatically, whereas with the state-of-the-art program, you have to look through over 300 strings. And what I mean by that is you have to actually reverse the binary and look through it. So yeah, in conclusion, this is the first generic fuzzer-based backdoor detector and also the first backdoor detection benchmark. We detect all backdoors in it in an hour 30 minutes on average with 7 inputs to vet on average, which is 44 times less positives without reverse engineering, without the source code. Thank you.
We've got plenty of time for questions, so I see some.
Yeah, I have a question about, is it on? Yeah, okay. What kind of techniques do you use to force the code to run through these paths? In general, it's not computable, probably. You cannot, even if you have the source code, there's no way to do it in full generality. So what kind of techniques are you using there to force ROSA to find these, the right state to enter these backdoors, these potential backdoors?
Right, so the guidance is fully on the fuzzer side, right? So we don't actually change how AFL++, in this case, goes through the code. AFL++ has like a decade's worth of good heuristics to go through most of the code, if possible, all of the code. So that alone seems to be reliable enough to trigger all different behaviors.
I have a very basic question. You showed the backend router as an example. How did you get the backend router software web server to run on another system?
So that's thanks to QEMU, right? So since we're in a binary-only setting, a fuzzer like AFL++ needs some feedback from the target. Obviously, if you have a binary, you can't get that. So you either rewrite it, basically, or you run it through an emulator, and that's what we use here. So the advantage is that you get any piece of information you want. The disadvantage is that it's slow. That's why it took 4 hours for Belgium.
I have 2 questions. The first one is you mentioned it's very well detects like hard-coded credentials. What about like if like it's a little bit smarter, like if the input is like an algorithm, like a key generator, like if the input checksums to a specific thing? Or this is the first question. And the second one, your example shows S-trace, and like I assume like ROSA also uses S-trace or how to collect the system calls, and it's quite common for like hidden backdoors to detect that the program is under S-trace and to not reveal behavior. So how is that addressed? Or is it?
So for the first question, so we don't only detect hard-coded backdoors. So, and in fact, we have multiple backdoors in the benchmark that are done on purpose without using hard-coded credentials. The magic there is basically from the fuzzer, right? So the fuzzer has heuristics to help it solve this magic byte problem where, yeah, you can depend on some lightweight obfuscation, let's say, stuff like that. If you go much further than that, there's actually like fuzzer blocking techniques. For example, you can hide something behind a cryptographic check. There's no way for a fuzzer to go through that, obviously. But that is generally something that's hard to detect with dynamic analysis. And oftentimes, it might be also hard to detect via static analysis for different reasons. So that's kind of the general blocking point. For the second question about S-trace, so ROSA does not actually use S-trace. ROSA relies on QEMU, and we just literally like save the register value, right, when it syscalls. And yeah, sure, you have programs that use S-trace. I mean, that's another limitation, let's say, of the tool. Maybe you can't detect those. But for the ones that don't, which honestly all of the real ones that we tested don't, you can detect. So. Yeah, oh, that's another idea, yeah. Well, I was working on a prototype actually with that, but then you're limited to specific systems. So you have a trade-off.
Thanks a lot for the presentation, a really interesting approach, really like it. I've got one question, which is why the 2 repositories are archived?
So it's because the reason why we couldn't compare to the state of the art is that none of them were archived. So in my opinion, if you want to do science and do it well, you have to archive everything. You have to make it available.
GitHub style archive. They're not archived in the GitHub sense.
Right. They're archived in the proper sense. So they're archived for forever. They're archived for people to be able to use far in the future so that you can replicate with the exact commit hash that I used and so on. So that's the point behind archiving.
Okay, thank you. We are out of the time. Thank you for the presentation.
Thank you.